today we'll be looking at operational amplifiers. So the learning outcomes for today is we'll have a look at some basic electrical components and some semiconductor technology. We'll then move on to op-amps, and we'll look at what an op-amp is and some of the basic functionality transfer functions of these, and we'll look to design some circuits around op-amps. And then we'll finish today with looking at the limitations of op-amps in reality. The exercises for today will be learning a circuit simulation program. So this first video will look at basic electrical components. So for our mechatronic system, we're going to have some sensors and we're going to have our controller. And what we're going to need between our sensors and our controller is some electronics. And these electronics are to condition the signal to be at an appropriate level for our controller to input. So there's various reasons we might need the signal conditioning. We might want to change the signal level. So our sensor, for example, may give out millivolts, and we would like to amplify that into volts. So we properly use our circuits for amplification. We can use our circuits for noise reduction. So if there's background signals on that signal, what we can do is filter some of that noise out. The right type of signal, so sometimes we don't have an electrical signal, well, we don't have a voltage signal we want to measure. It might be, for example, a resistance, and we want to change that into a voltage so we can read that into our microcontroller. We had to look at this last week when we looked at our Wheatstone bridge, so it's that type of scenario we're considering. There's protection. So in case we have high voltage or high current levels, we don't want to damage our controller, so we can have circuits prior to that to protect our controller. And also signal manipulation. So our signal might be encoded in some way and we want some electronics to decode that. So there's various reasons why we'd have some electronic conditioning prior to reading the signal into a microcontroller. So in terms of our basic electrical components, so this is our starting point. You'll recognize some of these. We have got our basic resistor, our capacitor, so this will be a way of storing charge. An inductor, this is essentially a coil of wire. A diode, this is essentially a one-way device for current. And a transistor, which is essentially an amplifier. So we'll have a look at each of these components. So let's take the basic components first of all, a resistor, capacitor and inductor. And what we'll do is we'll apply a voltage across these, and this will be an AC voltage. So it's a sinusoidally varying voltage that we're applying across the components. It's also going to have a corresponding current going through, which will be sinusoidally varying as well. So for the resistor, we put this voltage across, it gives a corresponding current through this, and the resistance is defined by Ohm's law, V equals IR, so the resistance is the voltage over the current. When we come to our capacitor, we put in a voltage across the capacitor, but the current flowing through our capacitor is equal to the rate of change of voltage across the capacitor times its capacitance. So if we substitute our voltage here into our dV by dt term and do the differentiation, we find this is the current going through our capacitor for that voltage. So what you find is there's a J term in there, so it's a complex number. And what this means is there's a phase difference between the voltage and the current. Now we've got the voltage and the current, we can work out the resistance. And because it's complex, we don't say resistance, we say impedance. So the impedance of this, or its resistance to having current flow through it, is again voltage divided by current. Our voltage is this term here. Our current is now this term. So 1 divided by the other, cancel out common terms, and you get 1 over j omega c. So the impedance of a capacitor is inversely proportional to the frequency of the electrical signal. So as the frequency goes up, the impedance of a capacitor goes down. So I will just clear that. Restart. Okay, so for our inductor, we're passing a current through our inductor. So our current we're passing through is a sinusoidally varying current. The voltage across the inductor is the rate of change of this current times by the inductance. So we can substitute I in there, differentiate, and we get this term out. Again, we can find the impedance of this inductor, V over I. So we're putting our V over I in here, and we get j omega L. So in this case, as the frequency goes up, the impedance of the inductor goes up. So for our 3 cases, for our resistor, the resistance is always constant. For our capacitor, the impedance the impedance decreases as the frequency increases. And for our inductor, the impedance increases as the frequency increases. So this is in the frequency domain. So we've got omega equals 2 pi f. So we're talking about that in terms of frequency. We can also work in the Laplace domain. And in the Laplace domain, it's represented by these terms here. So the impedance is 1 over SC, and for the capacitor, and for the inductor, the impedance is SL. So we will be predominantly working in the frequency domain, so we will be working in this domain here. The Laplace domain, for the purposes of this module, is useful because we'll use this on MATLAB to just model some of the transfer functions. So I'm just mentioning it here in passing. Okay, so let's think about some other components that we might use. So diodes are essentially, they look like this. And what these are is a one-way system for current. So you can pass current through in that direction, but it resists current going in the opposite direction. So we have this as a typical IV plot for a diode. You don't get any current flowing through the diode until you reach a certain voltage level, and then once you reach a certain voltage level, it easily passes current through it in that direction. It resists current in the reverse direction, so you might get a slight bit of leakage current, but predominantly it resists current flowing in that direction until you reach a certain voltage level. And at this voltage level, known as the reverse, the breakdown voltage, reverse bias breakdown voltage, then this will break the diode and you'll get current flowing in that direction. So typically you operate diodes in this region here. Prevents current flowing in reverse, but easily allow current flowing in the forward direction. If you look at the characteristics of a diode, if you put a voltage in the forward direction, so this blue line here, and then switch to reverse direction, it allows current to pass in the forward direction, which is this part here. When you switch it, it should actually prevent it in the reverse direction. But there's a recovery time associated with diodes, so for a small fraction of time, it will allow current in the reverse direction before it recovers and then prevents current. And this delay is known as the recovery time of a diode. And the diode is formed by 2 pieces of doped silicon, so P doped and N doped. You join these together to form a junction, and that is your diode. It's used to control back EMFs, so we had to look at that when we looked at motor control in instrumentation and drives. We can also use it to rectify signals. So if you have an AC signal going plus and minus, you can put that through a a diode bridge, and what happens is it makes all the signal positive like that. So that's the typical use of diodes. As I said, if you connect them in reverse, if it's too large reverse voltage, you'll actually break them. And in reverse, it's a finite recovery time. So it will leak a little bit of current until it recovers and then stops the current flowing. Typically, diodes are made from germanium or silicon, but you can get more specialized ones. So in the case of Schottky diodes, this is a metal on a semiconductor. So they got the same operational characteristics as a normal diode, except they've got a very low forward bias. So in order to get current to flow in the forward direction, you don't need much voltage to get this current flow. And you've got a very fast switching time, so there's virtually zero recovery time on these things. So you can think of Schottky diodes as very high performing diodes. Zener diodes are a very special case of diodes, and Zener diodes are designed to work in reverse bias. So we said current is supposed to flow forward through a diode. In this case, we connect the diode in reverse, so current flows in the wrong direction. And what happens is the voltage across the diode reaches the reverse breakdown voltage. So the diode's essentially failed and current is flowing in that direction. It doesn't break the diode, but what it does mean is that this reverse voltage is at a very specific value. So typically it's something like minus 1.2 volts or thereabouts. So the Zener diodes are designed to break down a very specific voltage. And what this means is when they connect it in reverse, you can use them as a voltage reference source. So you have a very precise voltage measurement that you can use to reference other voltages to. So we'll come across an example of this when we discuss voltage regulators. Light emitting diodes, a special kind of diode. It's a normal diode that's doped with usually gallium. And when you pass current through it, it emits photons. So you're getting photons emitted, so it's emitting light. This is what an LED looks like. So you're all probably familiar with LEDs. The anode is the slightly longer contact. So the slightly longer contact. Just get rid of that. Restart. So the anode is a slightly longer contact on this connection. You've got large activation voltage, so you have to have enough voltage across them to actually pass current. You also have to be very careful at passing current through these because too much current will break them. So what you tend to do is put a resistor in series with these to limit the current. Photodiodes are the complementary aspect of the LED in which they absorb photons, so they're used to measure light levels. When photons fall onto a photodiode, the resistance drops, and therefore for fixed voltage across the photodiode you get a large current. They have a very fast response, so they're typical of that. And what you can either use photodiodes to measure light directly, or they're commonly used with LEDs and what's known as optocouplers. So if you want to pass a signal across somewhere and you want to totally electrically isolate both sides, you can generate photons on one side of the circuit with an LED and then measure that signal with a photodiode on the other circuit, so there's no hardwire connection between the two circuits. And again, we'll come across an example of that later on when we talk about noise and circuit design. So moving on to transistors. A transistor is essentially two diodes stuck together. So if you take two diodes and stick the P-doped material together, you get an NPN. If you take two diodes and stick together the N-type material or the N-doped material, you get a PNP. And a transistor is essentially an amplifier. And what you have is this arrangement. So this is an NPN arrangement. And in an NPN arrangement, you put a voltage across. So you put a voltage. So this is your voltage up here. And you ground on this side. You put current into the base on your NPN. And a small amount of current going in here results in a large amount of current flowing through here. These are known as current sinks because when you use an NPN, your load, whatever you're trying to drive, for example, a motor, goes on this side of the transistor. So the current coming from the motor is synced to earth. So that's why they're known as sinking current. For a PNP, it's a similar arrangement. So you've got the voltage up here, the ground on this side. In this time, the base, the current in the base is in this direction. So you have current coming flow through here. Some goes that way and the rest goes down to the collector. And in this case, you would attach your motor to the ground side of this connection. So these are known as current sources because the source of the current is coming through here to the motor. So as I said, a transistor is just an amplifier. So when you put current, I just escape that. When you put current into the base, here, a small amount of current, you get a large current flowing through here. So depending on the voltage you've got across the collector emitter contact, so if I put a voltage say here, then depending on the amount of base current you have going out, you're going into the transistor, you get a certain amount of collector current flowing through the transistor. And this amplification is typically a few tens to maybe up to 100 times. What you can do, what's commonly done, is you operate a collector emitter voltage around this region, which corresponds to the saturation region. So basically, you're using this as a switch. So you put a base current in there, and then you're getting your full current out through your collector emitter route. So typically they're used with a significantly high enough voltage that you're in this region. So it's not that high, it can be 5-10 volts, but you operating this in saturation, so it's essentially, rather than being an amplifier, it's essentially a switch. So the transistor is either switched on or switched off. Now what you want, or a typical use for transistors, is to power motors. So you put your current in, your transistor, you have your motor connected here, your voltage source. There's no current flows, you're operating it as a switch. So you put some current in there. Current is then allowed to flow through the motor and down to earth, and the motor turns. The slight problem with this scenario is because we've got a limited amount of gain on this, then in order to drive enough current through here, we also need a significant amount of current through here. And if you're using something like an Arduino to drive this transistor, then that isn't going to be much current coming in here. So ultimately, we're not going to get enough current going through the motor. Power transistors are two transistors connected together. So you can see this is an NPN arrangement here. And what we have is a small base current coming in here. This then drives a larger emitter current here, which then forms the current to going into the base of a second transistor. So then the current flowing, so our motor might be here, the current flowing is now significantly larger because we're getting two lots of amplification. through the system. So this is your power transistor arrangement, where you have them, where you're using multiple transistors to amplify the current to get enough current through. So that is your NPN, where you've got two NPN transistors connected. You've got a PNP arrangement here, where you've got one PNP and the other one is an NPN to lead to a PNP power transistor. Because you've got a large current flowing through these, then you're going to generate a lot of heat. So you typically have these on either a metal plate or a heat sink to try and dissipate some of this energy. So they were known as bipolar transistors. So they're made of doped silicon, p-doped and n-doped silicon. There is another type of transistor called a field effect transistor, FET. So in this case, it's a MOSFET, or metal oxide on semiconductor field effect transistor. They essentially do the same job, where they're amplifying a current, except they work in a slightly different way. So for the transistor, we had a collector, a base and emitter. For our FETs, we have a drain, a gate and a source. And rather than putting current in the case of a FET, what we do is we set this at a certain voltage level. So we might set this, say, 10 volts. When this is activated to be a certain voltage level, then this essentially opens this route up for the current, and current's allowed to flow through here, and hence we've activated the transistor. So these voltage operated rather than current operated transistors. Because of that, they're conceptually easier to use, because we don't have to worry about sourcing or sinking current in our circuit. All we have to do is generate a voltage at this gate in order to operate the transistor. So MOSFETs tend to be higher or better performing transistors compared to their bipolar counterparts. So that concludes a brief introduction to some of the electrical components. So in the next video, we'll move on to one of the most commonest types of electrical component that's used, and that is the operational amplifier.